All right, we're continuing with Chapter 4 in the trigonometry textbook. Chapter 4 is on the graphs of circular functions. That's when we think about circular functions, we're thinking trig functions in radians. In this video, we're going to go through section 4.2, which is on translations of the graphs of the sine and cosine functions. So in the opening section, we looked at sine and cosine functions with all possible transformations except for translations, horizontal and vertical translations. So we considered scaling about the x or y axis, and as well as flipping about the x or y axis, or any combination of all of those. But we never considered any type of translation. So now in this section, we're going to bring everything together. We're going to add in the potential for horizontal and vertical translations. And so that this will complete, the full analysis of the sine and cosine functions. Okay, so if you need to go review how functions and equations are transformed, go check out the algebra playlist. There's a few videos on this, and this will be really helpful for you as we go through this section and work example problems, in particular because it gets a bit confusing. If you just have scaling or flipping, it's not that confusing. But when you start mixing in translations in combination with scaling about the same axis, scaling or flipping about the same axis that you're translating, it can get a little confusing. And so what I'll do is there's a video from the algebra playlist that summarizes how this could be confusing, and I'll put that a link to that video in the description. But it's all in the algebra playlist, so it would be helpful for you if you even if you've already seen those videos, go rewatch them. Okay, and as we go through this video, I'll talk about some of the confusing things about these mixed in transformations. Okay, but so all right, it starts off with horizontal translations, and as we know, for if you have any function or equation, like I'm saying equation, maybe you have an equation that's not a function, it's a relation. What you do is you go to every single x variable in the entire function or relation. There might be more than one x variable. Well, with the sine, with the basic sine and cosine, there's not. But just thinking about transformations in general, you go to every single x variable, and I'll write out let's put sine here. But again, you could have multiple x variables all over the place. So if you want to just do a rigid body shift of the graph horizontally, you go to every single x variable and replace that x variable. That's a good way to think about it. Not just subtracting a constant or adding a constant to the x variable. It's kind of like you replace the entire x variable with. So if I wanted to shift the sine curve to the left 5 units, I would replace x with x plus 5. Or, add 5 to x, but, again, if you say replace it, I think that's kind of helpful to think about, saying you erase this and replace it with x plus 5. So it's like the opposite. If you would think, oh, this is going to shift it in the positive direction. Well, no, it's the opposite. Okay. But again, if there was more than one variable, if you had like x cubed minus absolute value of x and then plus x squared, something like that, and you want to shift this 5 units to the left, you would do right. And same thing with like a relation. If you had x's and y's all over the place on both sides of the equation, just go to every single x variable and replace it with what you want to shift it with. Okay, but for just the basic sine curve, this is how you shift it. There's one x variable, just replace it with, you're adding or subtracting the amount that based on how much you want to shift it. Now, what we want to think about is, as we're going through this section, is so in the previous section we would apply the scaling and or the flipping, and we drew the resulting graphs. But then when we were done, we always talked about what's the resulting the final graph. What's the period, frequency, angular frequency, amplitude, and we saw how scaling about the x or y axis and flipping about the x or y axis, we saw how that affected these parameters, and really flipping didn't do anything. All things being unchanged, if all you did was flip the graph about the x or y axis, it didn't change the period, the frequency, the angular frequency, or the amplitude. It was only the scaling about the x and y axis, and yeah, only the scaling about the x or y axis changed those parameters. So what is a horizontal shift of a sinusoid, right? What's that going to do? Is that going to affect, well, what does that affect? So let's think about the sine curve. Well, if you shift it, a rigid body shifts horizontally, that's, you can think about, that's not going to affect the period or the frequency or the angular frequency or the amplitude. It's not going to affect any of those parameters. Okay, so but does it affect anything? I mean, how do we talk about the change in the graph when you shift it horizontally? Well, the idea is that, you know, what we kind of talked about was that the pure definition of a sine function is that it's like at the origin, at x equals 0, it's starting at 0, and then when you go in the positive direction, it's on the upward, it's going upward towards the positive amplitude, right? And then the cosine at x equals 0, it's starting at the positive amplitude, and then it's on its way down. Right? And so if you shift any of these curves horizontally, it's like you're moving away from the pure definition of the sine or cosine towards the other, like, okay, if you shifted cosine to the right a little bit, well, then it's kind of like you don't have a pure cosine anymore. It's you have a percent. It's like a percent cosine. And once you cross that halfway point, so this should be pi over 2 apart, I believe, this here to here. Once you get past pi over 4, it's like you're more of a sine curve than you are a cosine curve, right? It's like you could. That's one way you could think about it. Now, the way that this is the really the more official math way to talk about this is with the term phase shift or phase, and that just tells you, you know, if you can have a sine or cosine function, and it's going to have a phase in it. In this case, the phase shift would be 5, and that's just telling you how far shifted you are from the pure sine or cosine function, whatever one you have. Okay, so you could see phase shift here, right? A horizontal translation is a phase shift, and I think that this is called the phase. I'll have to look up the exact terminology, but yeah, that's the phase shift tells you how far away you are from like the pure definition of sine or cosine. Now, just note that this term phase or phase shift, that's not unique to that's applied to any periodic function, not just sine or cosine. So a square wave, whatever, you can think about it being having a phase shift. All right, so it says in the function y is equal to f of x minus d, the expression x minus d is the argument. So yeah, in any function, this is the what you plug in to the function is the argument. So x plus 5 is the argument here. Okay, graph y is equal to sine of x minus pi over 3 over 1 period. So yeah, when we go to graph these, when we work example problems for graphing these, there's two methods that the textbook gives. And so there's one method that I really like, though I think is really intuitive. Let's see, method 1, for the argument x minus pi over 3 to result in all possible values throughout 1 period, it must take on all values between 0 and 2 pi inclusive to find an interval of 1 period. Yeah, so I like this first method. What we're going to do is, if we want to consider for the graphing a horizontal shift, what we did in the previous video was we started by determining the period, right? So if the function was scaled about the x-axis, the period might be different from the standard period of 2 pi. Here the period is just still 2 pi. And then the way we did it was there was no horizontal shift, and so we like started at 0 and then went a period in the positive direction and then sketched a period and then copied and pasted the period throughout the rest of the graph, right? With a horizontal shift, when there's a horizontal shift, all we're going to do is we're going to think about like that interval from 0 to the period, 0 to 2 pi or 0 to pi or whatever, 0 to 4 pi, whatever it is. We're going to think about that interval being shifted. I'm going to call it a sketching interval. That's the sketching interval has been shifted, and then we're going to sketch the curve through the sketching interval and then copy and paste it. But just it's important to note, though, that there's really no such thing as like a period interval, right? I mean, like we think about the cosine curve and the sine curve starting at x equals 0. That is true, but a period can go from any point to any point. You pick, like, you could have a period on a sine curve going from 1 to 1 plus 2 pi, right? There's no actual period interval, but just we use that. A lot of times we think about a period starting at like the origin. So whenever we have a horizontal shift, we're going to follow where that origin shifted to, and then sketch the period from there, because it's going to be easy. We're going to know that, okay, at the new hypothetical origin point, we know the sine curve starts at 0, and the cosine curve starts at the positive amplitude. Or if there's a flip, then it'll start the negative amplitude, right? So that's how we're going to sketch these curves. But it gives another method here. Yeah, you could see there's sine of x, and there's the sine of x minus pi over 3. What we're going to do is, you could think about, well, it'll be slightly different than this, but like we're going to sketch. We know that the starting point got shifted in the positive direction pi over 3, and then so we imagine the new 0 point is pi over 3, and the new end of the period point is 2 pi plus pi over 3, and then we sketch this just like we did in the previous section, right? And then we can copy and paste this all the way up and down the x-axis as far as we need. But it'll be a little bit different because we're going to stop at, the graph's going to stop at 2 pi. It's going to go from, like, in this situation, it would go from negative 2 pi to 2 pi. So this is we want to sketch a full period on the graph. So we'll kind of look at the period from minus 2 pi plus pi over 3 to 0 minus pi over 3, and we'll sketch that. Or no, it would be, yeah, it would go from minus 2 pi plus pi over 3 to pi over 3, and sketch that. Okay, but so method 2, we can also graph y is equal to x minus pi over 3 by using a horizontal translation of the graph. Yes, I mean, this isn't a bad idea. What you could do is you could sketch, we could start off by just sketching the curve like we did in the previous section without the horizontal shift, and then like kind of copying and pasting, like do that on another layer, on a separate layer on your computer screen, and then take that layer and shift it, and then you have your graph. That's actually not a bad method either. In some of the example problems, I might do that as well just to show you, but whatever you want to do. But the tricky part is again, it's those transformations mixed in, like scaling or flipping mixed in with the horizontal shift, and it's the same idea with the vertical shift. So, all right, let's see. In the example 1, the argument of the function is x minus pi over 3. The parentheses are important here. If the function had been sine of x minus pi over 3, the graph, yeah, this would be a vertical shift, whereas what was shown here is a horizontal shift. Okay, whenever we're analyzing an argument, this one was easy. It was just x minus plus or minus a constant, and that was it. But again, it's once you start mixing in, flipping, or scaling about that same axis that you're translating. So what if we had sine of 2x minus pi over 3? How do we view this? Has this been shifted pi over 3 units to the right? Well, no. What you want to do is you want to get a coefficient of 1 in front of the x variable, or minus 1, depending on how you look at it. If there's flipping about the y-axis, means there's a minus kind of multiplying the x variable. Then there's a couple ways you could do it, but here there's no flipping here about the y-axis. So in general, you want to just get a 1 or a minus 1 in front of the x, and I'll explain the minus 1 in a second. Here, there's no minus 1, doesn't come into play anyway, but you want to do this. So factor out the 2, and you have x minus, and then this would be what? Pi over 6. So you distribute that, you have 2x minus pi over 3. And now, with that coefficient of 1 in front of the x, now we see what the shift is. It's pi over 6 to the right. It shifted pi over 6 to the right, and then it scaled up too. Like you can imagine, it would be like if we had a square root function, let's say, at y is equal to square root of x. You shifted it, let's say we had, it scaled down too. Sorry, it scaled. This is reciprocal of 2. Let's say we had, so y is equal to square, or 2, let's see. 2 times the square root of 2 times x minus 3. What that means is you've shifted this to the right 3 units, okay? And then, like, without moving the origin point, you scaled it down too. So you about the x-axis. So that would kind of look like it would seem like you kind of scaled it up about the y-axis, when in reality you've really just shrunk it in. Okay. Now, when it comes to the flipping about the y-axis, you can, so if we had, let's see, if this was a minus 2 here, there's 2 ways you can look at that. You can say that, so you can factor out a minus 2, and then you've got x plus pi over 6. And then the way you look at this is you shifted it to the left pi over 6. Then, without moving the origin, you scaled it down by a factor of 2. And then you flipped it about a y-axis that was like shifted with the origin. So thinking about the square root of x, if we had, what did I do here? I said y is equal to square root of, if it was minus 2x minus 3. Okay, this would be like you started with square root of x, you shifted it to the right 3, then you scaled it down by a factor of 2, then you flipped it about like an imaginary y-axis that's been transformed. So it would be kind of like this. Okay. Now, you could also write it like this. You could just factor out a 2, and then you would have minus x minus pi over 3. And that is saying that you shift it. So, okay, if we come to y is equal to square root, let's do this. So 2 minus x minus 3. That's like you have square root of x. You started with that. You shifted it to the right 3. Well, okay, if I would do plus 3 here to kind of make it. You could do minus 3, but the idea is I'm saying that if I'm imagining we didn't factor out a minus. Previously I did, what was it? It was 2 times x minus 3. No, it was minus 2 times x minus 3. So the x became positive, and there was a negative in front of the 3. So now if I'm not factoring out the negative, the x stays with the negative and the 3 stays positive. Okay, but you could still interpret it the same way if there was a minus in front of the 3. But so you shift it to the left 3, so it's over here, and then you flipped it about the original y-axis. So it comes here, and then you scale it down by 2, so you get the same result. Why do you get the same result? Because it's the same. I just want to illustrate that the first example that I did was y is equal to, all right, it was, what was it? 2x, yeah, it was minus 2x plus 3, right? Imagine we're starting with this. So you factor out, the first example was you took out a minus 2 and you get x, oh no, it was minus 2x plus 6. You took out a minus 2 and you get x minus 3, minus 2x minus 3, right? Or you could have not factored out the minus and get minus x plus 3. And you see it's the same result. It's just one, you're flipping about the original y-axis, and here you're flipping about a transformed y-axis. So it's however you want to look at it. If you're confused, go go watch that video. I'm going to post a link in the description. Okay, but like here, there's no confusion here because there's no flipping or scaling mixed in with the shift. So this is, we'll see how to sketch these. We just talked about how to sketch this, but the amplitude is going to have changed, but that's it. Amplitude is scaled up to from 1 to 3. Okay, here we've got, so how would we view this? All right, well it's been flipped and scaled up about the y-axis. No, it's been flipped about the x-axis, then scaled up by a factor of 2 about the y-axis. And then we would just write this. So to see the horizontal shifting, we would do this. Minus 2 cosine, and then there's no negative to consider, which is nice, flipping. So we take out the 3, and you get x by itself with a 1 or a minus 1 in front of it, plus pi over 3. And so there you go. It's been shifted to, you can see it's been shifted to the left pi over 3. Now again, if there was a negative to deal with, then you can factor out the negative, and the shift is going to be in one direction, or not factor out the negative and the shift is going to be in the other direction. But it all results in the same thing because you're either going to be flipping about the original y-axis or a transformed y-axis, so you get the same result. It's just, right, you're going to get the same sketch either way. It's just how you want to look at it. But in this case, there's no negative, there's no flipping. It's going to be shifted to the left pi over 3. Okay, but then you look at this though, the 3 tells you that it's going to be scaled about the x-axis down by a factor of 3. And you can think about that. It's that scaling is done without, imagine like before shifting, you can think about it. That's one way to think about it. Before shifting, it's scaled. But you could also think about it that it's shifted horizontally pi over 3 and then scaled, but without moving that origin point. It's like so you started with minus 2 cosine x. So that's like, and then you could think about so that the minus 2 is applied, you horizontally translate it to the left pi over 3. So now it's, and then you stretched it, or you shrunk it about the x-axis by a factor of 3. And so you typically, if you just put like a 3 in front of the x, it'll move the origin point too. Like the origin is at minus pi over 3, kind of that starting point. It would multiply that starting point by or divide that starting point by 3 as well, but it wouldn't do that. It would kind of like you imagine that the origin has like shifted with it, and it's going to scale it about this down by a factor of 3. Or if that's too confusing for you, then just imagine you apply the scaling first with the graph at the origin, then you shift it. Okay, vertical translations. And what I like about all those details of transformations of graphs that I'm talking about, it might seem confusing to you, but what I really like about learning that is it makes it's you can apply that universally to the x variables or the y variables in a function or equation. So right, you can think about replacing the f of x in a function with y, and then everything all the rules that we talk about that we just talked about with the x variables apply to the exact same way to the y variable, exact same. And it's not just with a function. You could have any kind of relation with all kind of stuff going on. X squared plus y squared is equal to 6xy. They both have the exact same translating scaling rules. You might say, well, no, I thought don't we add, when it comes to shifting about the y-axis vertically, don't we add the amount? It's like it's not the same as the x variable. No, well, it's like if you had y is equal to sine x, okay? We know if we want to shift about the x-axis to the in the positive direction 5, we subtract 5 from x, or replace x with x minus 5. Well, same thing. We replace, if we want to shift vertically, if we want to shift up about the y-axis, we subtract 5 from y. And what's the result? See? Same exact rules. They both have the same exact rules. If we wanted to scale the amplitude up by a factor of 2 and shift vertically upward 3, then we do this. We do 1/2, because we want to scale it up. Y minus 3 is equal to sine of x. That's it. So you multiply both sides by 2. Add 3 to both sides. And there you go. Okay, now, so if you have a vertical shift, how does that affect the main parameters of the sinusoid? Well, you can think about, so if we go from, let's see, if we look here, this is 3 minus 2 cosine 3x. Okay, the period has been scaled down by 3, so it's, what is it, 2 pi divided by 3. The amplitude has been scaled up by 2, and then it's been flipped. So you could think about it, but the vertical shift, it doesn't change the period, the frequency, or the angular frequency, right? And it doesn't affect the phase shift, obviously. That's like intimately related to the horizontal shift. But it doesn't change the amplitude either, okay? Because look, remember, the amplitude is the peak minus the valley. That distance is the amplitude. Well, the vertical shift doesn't affect that, right? And the reason why these shifts don't affect those parameters is because, remember, shifts have no effect on the shape of the graph. And period, frequency, angular frequency, amplitude, those are all related to the shape, right? Now, okay, but is there like a parallel to phase shift or phase with a horizontal shift? Is there something that kind of changes with regards to a vertical shift? Yes, there is. It's this you can think about this kind of mean point. That midpoint between the amplitudes changes. If with a non-vertically shifted sinusoid, that mean point is at 0, that midpoint. But with a vertically shifted graph, that changes. And this is an application of this is really evident with like fatigue. So you apply a fatigue load, and a lot of times it's sinusoidal. And what they talk about is like this is the load or the stress as a function of time, and you can have like there's fully reversed fatigue where it's the mean point is 0, but then you can have a mean load be non-zero, right? It's like that the average stress is some not zero value. Okay, but that's the only thing that changes with a vertical shift is that kind of that midpoint between the amplitudes. Okay, now how are we going to sketch this? What's the process we're going to use to sketch this? Well, let's see. So they say the method 1, which is the method that I liked when it came to the horizontal stretching, where we kind of imagine the interval, the period interval, the sketching interval to shift. So it says we use method 1. The values of y will be 3 greater than the corresponding values of y in y is equal to minus 2 cosine 3x. So yeah, what they're saying here is it's like you look at exactly what's been non-vertically shifted, and you'll get, if you kind of disregard the vertical shifting, you're going to get a sinusoid that's just like what we talked about for the horizontal shifting, right? We know how to sketch that, and you're going to go about the exact same process as you would. So here there's actually no horizontal shifting, but there might be. You're going to go about the exact same process, but then when you go to plot the points to draw the period, then you stop and say, okay, well, wait a minute, let's apply the vertical shift now. And so then when you put the, you might have you would have like the shifted the new shifted interval. So we're sketching from here to here, let's say, and then let's say it's a sine curve, and then you without the vertical shift, you would say, okay, this is the starting point, this is the ending point, and et cetera, but instead you would say, okay, before I plot that starting point, I want to apply the vertical shift. and then here I apply the vertical shift, and then here I apply the vertical shift, and then draw the graph that way. Now, with the second method, what they're saying you could do is you can draw the entire curve without the vertical shift, and then on like its own separate layer, and then move the layer up, apply the shift afterwards. So whatever you want to do. Now it says, okay, if we use method 2 to graph the function y is equal to 3 minus 2 cosine 3x in example 4, we must first graph and then apply the vertical translations 3 units up. Right. Because if they're saying when it comes to like a reflection, you need to, if you apply the reflection after the vertical shift, then you're going to reflect about the original x-axis, which wouldn't be accurate. And I mean, that's what, if you really watch that video that's in the description, go watch those translations videos and transformations videos, and you really understand the mechanics behind it and how it relates to the equation. You don't even have to worry about this. You could see exactly what's going on. It's everything we just talked about a few minutes ago. You could reorganize the equation and see, if you had, let's see, 2 minus 2x, no, it would be minus 2y plus 6 is equal to sine of x, right? Then it's the same idea. You can factor out a 2 or a minus 2, however you want to look at it. Let's do a minus 2, y, then minus 3, right? So in this case, it's like you started off by shifting the curve up 3 units, and then you scaled it down about the y-axis by a factor of 2, and then you flipped it about an imaginary x-axis that was shifted with the curve, okay? Or you can look at it this way. You could just factor out a 2, and then you've got minus y minus 3 is equal to sine of x. Okay, in this case, it's like you shifted it. Wait, this isn't right. It would be plus 3. Yeah. In this case, it's like you shifted it down 3 units. And then, I mean, you don't have to say, you could say, the order doesn't matter here, right? You shifted it down 3 units. Then you flipped it about the original x-axis in this case. And then you scaled it down about the y-axis by a factor of 2, but you don't apply that scaling to the origin point. That's the beauty of when you factor out, when you get the coefficient on the y on the variable with a 1 or the negative 1 or a 1, and you have it multiplying this like a full term like this, then that scaling isn't applied to like the shifted origin point, which is very intuitive. Right? In other words, you're not, if you shifted it down, you start off shifting the sine curve down 3 units. Okay? And then you apply you could scale it by 2 now, or you could flip it now, but you flipped it about the y-axis or the x-axis. Okay? And then, but like, I'm not going to draw that, but you scale it down by 2. Well, what you would think is, okay, well, it's going to scale this point down by 2 as well. This is 3. We're going to move this to 3/2, right? But you don't want to. You've already applied the vertical shift. I think that's why it's intuitive. You don't want to do another vertical. If you scale this origin point, like we've imagined that the x-axis has shifted with it. If you scale it down by 2, you don't want any vertical shift, right? That's because then it's like, wait a minute, I've changed the shift. You want to, okay, you shifted it by 3 down, scaled it by 2, but without shifting it vertically. And that's exactly the way you interpret this. Then you flip it about the original y-axis or the original x-axis. Here, it's like it's the same idea. This scaling of 2 is you do this. You shift it up 3. And then you could think about you scale it by 2 without changing that vertical shift. And then the minus on the outside means you flip it about this imaginary x-axis. So you get the same result either way. It's just two different ways of looking at it. Okay, so now they give guidelines here for sketching the sine and cosine functions, and we'll work example problems. You'll get the feel for the mechanics of this. Okay, so let's see here. We've got, how do we interpret this? Well, we can bring that y over, or that 1 over, so you have y plus 1. So that tells you the transformations that have been done to the y variable. Oh, well, no, not yet, not quite yet. So 2 sine 4x plus pi. We can divide both sides by 2. And again, you might be saying, well, why am I making this so confusing? It might seem confusing as first, but once you understand these transformations, it's like you've got so much more versatility to apply these transformations in any equation, in however many variables, more than 2 variables. I strongly suggest you watch those algebra videos and understand what I'm doing here, because your world is opened up to any equation with any number of variables, any relation that has, even if it's not a function, it doesn't matter. You fully understand how to apply transformations to about any axis. Okay, so there you go. We can see we've shifted down by 1 the sine curve, and without we scaled it up by 2, but without changing the shift. Right? That's like that, because that otherwise that wouldn't be intuitive. You shifted the sine curve down by 1. And then we want to scale it, but we don't want to change the vertical shift, right? Or else then it's like, it's confusing. Then it's scaled up by 2. So then it's like, right? Like that. Okay? But then there's also been some things done with the x direction. So what we want to do here is get that x variable with a 1 or a minus 1 in front of it. So x plus pi over 4. And there you go. So it's also been shifted to the left, pi over 4, and then scaled down about the x-axis by 4. Again, without, like, you can, this is the way you look at this. This is why this is so great. You take the original sine curve, and we can see we're gonna be shifting it to the left pi over 4 and down 1. Okay, that's where let's see. That's kind of like 1, -1, somewhere around here. So it's like we can do this in any order we want. That's the beauty of this, but let's look at it in this order. So we do the shifting first, then, so there's the sine curve. Okay, now the transformations are going to be applied without moving this center point. So it's going to be scaled down about the x-axis by a factor of 4, so it's going to be shrunken in, right? And then it's going to be scaled up about the y-axis by a factor of 2. So, like that. Very intuitive, right? Or you could do all the stretching and shrinking first, whatever you want. Start here, scale, do the scaling. And then do the shifting. So you shift it over here, and right? Okay. A trigonometric model for natural phenomena that occur in periodic patterns, such as seasonal temperatures, phases of the moon, heights of tides. A sinusoidal function will provide a good approximation of a set of data points. Yeah, so we mentioned this in the previous section, but any kind of purely periodic things in nature, right? The sinusoids are the kings of, or is the king, I guess the sinusoid is just one term, the king of the periodic function, right? Anything that you can think of that is just like, wow, that is as naturally periodic as it gets. Seasonal temperatures, phases of the moon, right? It's like the heights of tides. That's going to be sinusoidal. And you'll see with like Fourier transforms, that's a further illustration of why the sinusoid is the king of periodic functions. Okay, and we'll work some examples here. They're talking about the average monthly temperature in New Orleans. We'll get to see some real examples of sinusoid periodic patterns that have shifts on them, horizontal or vertical shifts, right? Because the average temperature isn't going to be at the mean point's not going to be 0 degrees, right? It's going to be shifted up, but we'll look at, okay, but what's the period? What's the frequency? What's the amplitude, right? What's the phase shift, if there is a phase shift? What's the new average, the temperature that's being or the value that's being oscillated about? Okay, so now let's work some example problems.